Welcome, stargazers, to the Sleepy Astronomer. Tonight, we'll drift gently through the mysteries of time, one of the strangest and most beautiful concepts in the cosmos. Before we begin, I'd love to know, where in the world are you watching from? Are you listening beneath northern lights, desert skies, or the soft hum of city stars? Wherever you are, get cozy. Take a deep breath. Let's explore a question that has puzzled physicists and dreamers alike. Could time ever run backward? Time is one of those mysterious things that we all experience, but few of us ever stop to truly understand. We live inside it. We measure it with clocks. We feel it passing in every breath and heartbeat. Yet when we ask the question, what is time? The answers slip through our fingers like grains of sand. Scientists, philosophers, and poets have pondered it for centuries, and still it remains one of the most elusive and profound concepts we know. At first glance, time seems simple. One moment follows another. The past is behind us, the future ahead. We remember what happened yesterday, we plan for tomorrow, and we live, always, in the fleeting sliver we call now. But when we look closer, we realize that this flow we take for granted may not be as solid as it seems. Time is not an object you can touch or hold. It doesn't have colour, weight, or texture. And yet, it governs everything. In physics, time is often treated as a dimension, much like the dimensions of space: length, width, and height. Just as we can move left or right, up or down, forward or backward in space, time might be something we could, in theory, move through, if only we knew how. Einstein's theory of relativity changed our view of time forever. He showed that time and space are woven together into a single fabric called space-time. And this fabric can bend, stretch, and warp depending on the presence of mass and energy. That's why time runs slower near a black hole or when you're moving very fast. Time, then, is not fixed. It is flexible, relative, and deeply tied to gravity and motion. But even before Einstein, people were wondering about time's strange nature. Saint Augustine, a philosopher from the 4th century, once wrote, "What is time? If no one asks me, I know what it is, but if I try to explain it, I do not know." That quote still captures the mystery we feel today. We intuitively understand time. We know what it means to be late, to wait, to grow older. But defining it in a precise way is incredibly difficult. Some physicists suggest that time might not even be fundamental. It could be a kind of illusion, something that emerges from deeper, more basic laws of the universe, just as temperature emerges from the movement of particles. From this view, time isn't a basic ingredient of reality, but a byproduct of something else, something we haven't fully uncovered yet. Maybe our brains, designed to make sense of change and motion, simply create the experience of flowing time to make sense of the world. Still, there's something poetic and powerful about how we experience it. Time is tied to memory. We know the past because we can remember it. We don't know the future because it hasn't happened, at least not for us. But what if that was only a trick of our biology or our limited perception? What if the past, present, and future all exist at once, and we're just moving through them like a needle through a record, hearing the song one note at a time. In some interpretations of physics, like the block universe theory, this is exactly what happens. The idea is that all moments in time are equally real, like scenes in a movie reel. The entire film exists, from the opening to the closing credits, but we only see one frame at a time. In this view, the passage of time is a kind of illusion, and all events, past and future, are fixed in place, just waiting to be seen. If that sounds strange or unsettling, you're not alone. Many people find it hard to accept a reality where the future is already written, and free will might not exist the way we think it does. But perhaps there's a kind of comfort in the idea too, a reassurance that every moment, even the ones we've lost, still exists somewhere in the cosmic library of time. And yet, for all these theories and poetic images, the truth is, we don't really know what time is. It continues to pass, quietly and steadily. It allows us to age, to grow, to change. It heals wounds, deepens love, and weaves stories. We build our lives on it, measure it in anniversaries, sunrises, and sighs. Even if we never fully understand it, time shapes every part of our reality. So as we float here together, under the night sky, let us wonder gently, what is time, really? Is it a river, a dimension, a trick of perception, or something even more mysterious than we can imagine? Close your eyes if you like, and let the question hang in the quiet air. There are no answers we must find tonight, only the joy of asking the question. If you've ever dropped a glass and watched it shatter, you've witnessed something very important about time, something so ordinary, yet so deeply mysterious. The broken pieces never leap back together. The glass doesn't unbreak. We don't grow younger. We don't forget memories we've already made. Time, it seems, moves in one direction, and only one. This forward motion is what scientists and philosophers call the arrow of time. But why does time have an arrow at all? And what gives it this particular direction, this relentless push from past to future? To begin understanding the arrow of time, let's think about what it really means. The arrow of time points from the past to the future, marking a clear distinction between what has already happened and what has not yet occurred. We remember yesterday, not tomorrow. We age, not de-age. Eggs scramble, but they don't unscramble. Smoke rises from a matchstick, but never returns to form a solid. This all feels natural to us. It's how we live our lives. But the reason behind it is far more complex than it appears. Interestingly, most of the fundamental laws of physics don't actually care about time's direction. Whether time flows forward or backward, the equations work just the same. This is true in classical mechanics, in electromagnetism, and even in quantum theory. At the microscopic level, particles don't seem to prefer one direction of time over another. If you watched a video of two atoms bouncing off each other, and then reversed it, you wouldn't be able to tell whether it was playing forwards or backwards. The laws are symmetrical, and yet at the macroscopic level, the level of glasses, people and galaxies, time clearly has a direction. So what's going on? The answer lies in a concept called entropy, a measure of disorder or randomness in a system. According to the second law of thermodynamics, entropy in a closed system will always increase or stay the same. It never decreases. This law gives us a kind of cosmic one-way street. While it's possible, in theory, for the particles of a broken glass to randomly come back together and reassemble it, the probability of that happening is so low, so staggeringly unlikely, that we never observe it. Entropy explains why things fall apart, why hot tea cools down in a cold room, why the smoke doesn't unburn every time energy moves from one place to another. A little bit is lost to disorder. The universe trends toward messiness. And in that trend, from order to disorder, we find the arrow of time. It's as if entropy gives time its direction, not by some force pushing it, but simply by showing us what's overwhelmingly more likely to happen. This also explains why we remember the past, but not the future. Memory itself requires order. Our brains record experiences by creating specific, structured connections between neurons. Once that structure is in place, we can recall the event, but the future, being undefined and full of higher entropy possibilities, has no such structure yet, so we can't remember it. The arrow of time is, in this way, also the arrow of memory, of cause and effect, of the way events build upon one another. Interestingly, the arrow of time is not necessarily universal in all aspects of the cosmos. Some physicists have speculated that, in far-off parts of the universe, or in the distant past or future, time might behave differently. It's even possible, though still theoretical, that in another region of the universe, time could run backward from our perspective. In such a universe, beings might remember what we see as the future and be puzzled by the unpredictability of what we call the past. But in our corner of existence, entropy defines the flow. We are passengers on a river that only runs one way. The origin of this direction might trace all the way back to the Big Bang. At that moment, the universe was in an incredibly low entropy state, dense, hot, and remarkably uniform. Since then, entropy has only increased. Stars formed, planets coalesced, life emerged, and with every step, the universe has grown more complex, more chaotic, more entropic. Why the universe began in such an unusually ordered state remains one of the deepest mysteries in cosmology. Some think it's just how things started. Others believe there's a deeper principle we haven't discovered yet. Either way, that starting condition set the arrow of time into motion. We often take the direction of time for granted, but imagine what life would be like without it. If time had no direction, or if it reversed unpredictably, our world would make no sense. We wouldn't know whether stepping forward would take us into the future or the past. Causes and effects could reverse. You might put a seed in the ground and watch a tree shrink into it. Or worse, you might unlive your own life, growing younger, forgetting everything, returning to infancy. But in the world we know, the arrow points forward, steady and true. Time's direction defines our lives. It gives stories a beginning and an end. It allows us to grow, to learn, to build. It gives us hope that tomorrow can be better than today, and meaning to the passage of experience. Without the arrow of time, there would be no history, no growth, no anticipation. Just a static moment with no direction, no journey, no life. So as we lie beneath the stars and wonder about time's strange, silent push. We can be grateful. The arrow of time, born in the early fire of the cosmos, flows through everything, from galaxies spinning to hearts beating. And though it may be invisible, we feel its motion in every second we live. If the arrow of time gives us a sense of direction, then entropy is the engine quietly driving it forward. Entropy is not just a scientific term. It is, in many ways, the hidden rhythm of the universe. It touches everything, from the way stars burn to the way our bodies age, from the fading of memories to the fall of civilizations. Entropy is the measure of disorder, but that word, disorder, doesn't quite capture the strange elegance behind this force. To truly understand why time flows forward and never in reverse, we have to dive into the deep and curious world of entropy. Let's begin with a simple thought. Imagine you have a perfectly tidy room, everything is folded, sorted, organized just so. Now imagine walking away from that room for 100 years, leaving it completely untouched. When you return, what do you expect to find? The chances are it would be dusty, maybe cluttered, maybe invaded by time, nature, or decay. Things fall apart. That's entropy in action. Left alone, systems tend toward disorder, not because there's some force pushing them to, but because there are vastly more ways for something to be messy than there are for it to be perfectly neat. In scientific terms, entropy is a statistical property. It's not about chaos in the dramatic sense, but about the number of possible microscopic arrangements a system can have. The more possible arrangements, the higher the entropy. Think of a jigsaw puzzle. When it's completed, it has only one correct form. But when it's broken into pieces and scattered across the floor, there are countless ways those pieces can lie. The scattered version has far higher entropy. Nature doesn't prefer it, it's just far more likely. This is where the second law of thermodynamics comes into play. In a closed system, where no energy enters or leaves, entropy will never decrease. It will stay the same or increase. This law is one of the most fundamental truths we know, and it holds up across the vast stretches of space and time. It explains why heat flows from hot things to cold things, why you can't unmix cream from your coffee, and why you'll never see smoke reform into a log in the fireplace. These aren't just everyday experiences, they're deep reflections of the universe's tendencies. Now, how does this relate to time? Entropy is the reason we can tell the difference between the past and the future. In the past, things were more ordered. In the future, they will be more disordered. It's that simple and that profound. The increasing entropy of the universe is what creates the flow we call time. Without it, every moment would be interchangeable. No beginning, no end, no story. Entropy gives time its flavour. It's what separates a memory from a prophecy. Let's zoom out to the cosmic scale. The early universe, just after the Big Bang, was hot, dense, and incredibly uniform. Paradoxically, that uniformity represented a low entropy state. There was little complexity, little variety. But as the universe expanded and cooled, structures formed, galaxies, stars, planets, and eventually life. All of this, surprisingly, represents an increase in entropy. It's a kind of ordered chaos, one that allows intricate patterns to emerge even as the overall disorder rises. Every burning star increases entropy by radiating heat into the cold vacuum of space. Every breath you take, every heartbeat, every chemical reaction in your cells contributes in some small way to the grand climb of entropy. You are a temporary pocket of low entropy in a universe trending toward more. But this brings us to a haunting thought. If entropy always increases, what happens in the very far future? Eventually, the stars will burn out, the galaxies will grow dark, black holes will evaporate, all usable energy will be spread thinly and evenly across space, unable to do work. This final state is sometimes called heat death, a time when entropy has reached its maximum and no more structure can form. The universe won't explode or collapse. It will simply become still, quiet, timeless. This distant future may seem bleak, but it's also deeply poetic. It tells us that the universe is like a grand unwinding clock, not ticking down to doom, but gently dispersing, letting go of tension, and surrendering to rest. Entropy in this sense is not destruction, it is completion. And yet, within that slow rise of entropy, life finds a way to dance. Our existence as conscious beings is a kind of miracle, a brief flash of complexity in an ocean of increasing disorder. Life thrives by feeding on differences, on gradients of heat, energy, and order. A tree grows by using the low entropy energy of sunlight and converting it into high entropy forms. A human mind organizes thoughts, forms memories, and builds meaning, all while contributing, inevitably, to the increase of entropy. There's a kind of wonder in that. Entropy doesn't just explain why time moves forward. It also explains how beauty, complexity, and even thought can arise in a universe that is, overall, tending toward disorder. We are part of that story. We are entropy's artists, sculpting moments of clarity out of the ever-widening sea of possibilities. So the next time you see cream swirl into coffee, or watch a sunset melt into twilight, think of entropy, not as an enemy, but as a companion. A quiet guide, reminding us that time flows in one direction, that moments are fleeting, and that every breath, every blink, every heartbeat is a tiny step in a grand cosmic unfolding. And somewhere, in the silence between seconds, perhaps there's peace in knowing that even the universe's slow fading is part of a deeper order, a kind of surrender to stillness, to balance, to the infinite. Imagine pressing a magical button that makes the entire universe run in reverse. Clouds reassemble into raindrops and fly upward into the sky. Broken glass leaps off the floor and becomes whole again. People grow younger with each passing moment, unlearning their experiences, their bodies becoming smaller, lighter, softer. Trees would suck carbon dioxide out of the air and pull sunlight back into the sky. Fires would unburn. Songs would unplay. Laughter would retreat back into the throat. This is the strange and wonderful idea of time reversing. But what would that actually look like? And more importantly, is it even possible? The thought of time running backward might sound like science fiction, but it's a very real question in the world of physics and cosmology. On the surface, many of the fundamental laws of nature are time symmetric. This means that, mathematically, they don't care whether time moves forward or backward. The equations that govern particles and forces still work if you reverse the direction of time. In this way, the universe doesn't demand that time only moves one way. So then why does it? As we explored earlier, entropy, the measure of disorder, is the main reason time seems to move forward. But suppose we could find a region of the universe, or even a whole universe, where entropy starts high and then decreases over time. In such a world, time would appear to run in reverse. Events that look impossible to us, unmixing, unburning, unbreaking, might happen naturally there, not because physics is different, but because the arrow of time has flipped. But let's bring this idea closer to home. Let's imagine what it would be like if our own world began to run backward. It would start slowly, so subtly you might not even notice at first. You might feel as though you're getting a little stronger, a little faster. Your hair, if greying, might begin to darken again. You'd regain old memories, but in reverse order, forgetting the most recent ones first. The food in your stomach would gradually undigest and return to its original form on your plate. Conversations would seem strange. People would appear to speak backward, words unforming from their mouths, returning to yours as if you'd never spoken them at all. Rain would flow upwards, rivers would reverse. Night would slowly become day, but not because the sun is rising. It's unsetting, climbing back into the sky from the horizon, casting shadows in reverse. Plants would pull their seeds back into the earth, closing their petals one by one. Birds would fly backward. All of this would feel deeply unnatural, even haunting. But what about the deeper consequences? If time reversed, we would not simply watch events play backwards. We would experience them in reverse. You wouldn't just see yourself growing younger. You would believe you were aging normally. Your thoughts, your sense of now, would reorient. In a reverse time universe, you wouldn't be aware that time was running backward at all. You'd experience the flow of time as you always have, forward from your point of view. You'd be building toward what we see as the past, but to you, it would still feel like the future. In this way, the idea of reverse time becomes even more fascinating. If our memories, identities, and consciousness flowed backward in perfect symmetry, we wouldn't notice anything unusual. You could live an entire reverse life and never question it, because every decision, every action would make sense in reverse. The moments of your life would still feel connected. What would seem strange to us as outside observers would feel completely normal to someone living within it. But this thought experiment raises deeper questions. Could such a reversed universe ever exist? Could we travel to it? Could we survive there? Some physicists think it's possible in theory. Certain solutions in Einstein's equations, particularly those involving closed time-like curves, allow for the possibility of loops in time, strange paths through space-time, where the past and future might blur together. In the world of quantum physics, particles sometimes behave in ways that seem to ignore the direction of time entirely. In some interpretations, a particle might influence its own past, or communicate information backward in time, at least in a probabilistic sense. These ideas are still highly speculative, but they suggest that time, as we experience it, might not be the whole story. There's also the notion that the universe itself might one day reverse. If the expansion of the universe were to stop and begin contracting, a scenario known as the Big Crunch, some have speculated that time might reverse along with space. This would mean that after billions of years of stars, galaxies, and entropy rising, everything would begin moving backward. Entropy would decrease, structures would simplify, and eventually the universe would return to a single, dense point, like a mirror image of the Big Bang. But even here, the physics is unclear. Would time actually run backward in such a scenario? Or would it still feel like it's going forward, just in a contracting space? No one knows for certain. Our understanding of time breaks down at the extreme limits of the universe, where quantum gravity, black holes, and cosmic horizons distort everything we know. Philosophically, the idea of time running backward is equally compelling. What is it that makes the future feel open and the past feel fixed? Is that a feature of time itself, or of human consciousness? If we could somehow reverse time while retaining awareness of the change, would we feel trapped or free? Would we be able to change anything? Or would we be moving through predetermined steps, unable to steer? And then there's the emotional layer. Imagine watching your loved ones come back to you, moments replaying in reverse, people you lost returning, lives lived backward until their first meeting with you, and then disappearing as they unmet you. The very concept challenges our deepest instincts about what it means to live, to remember, to let go. Ultimately, the idea of time running backward isn't just a physical question. It's a reflection of our longing to understand ourselves in the vast, mysterious tapestry of the universe. It speaks to our desire to undo mistakes, to revisit moments, to grasp time not as a river we're helplessly carried by, but as something we might one day understand, or even guide. So, could time ever run backward? The laws of nature don't rule it out. In some strange corner of reality, or in some distant future, we cannot yet imagine, maybe, just maybe, it already does. At the very beginning of everything, before stars, before galaxies, before atoms, there was a moment so profound and so mysterious that even now, billions of years later, we are still trying to understand it. That moment is known as the Big Bang, not an explosion in space, but the expansion of space itself. A beginning not just of matter and energy, but of time itself. And that simple idea that time had a beginning is one of the most astonishing revelations in all of science. To imagine the Big Bang is to attempt something nearly impossible. To picture a universe that did not yet exist, and a moment in which time was not yet ticking. It's not that the universe was small and compact and suddenly exploded into empty space. Before the Big Bang, there was no space, no time, no before to speak of at all. Time itself began in that moment. This isn't just poetic language, it's what modern physics, especially general relativity, leads us to believe. So how does this connect to the question of time running backward? To understand that, we need to consider what the Big Bang really was. It was a state of incredible density, temperature, and most importantly, low entropy. That's a curious thing, because when we think of something hot and chaotic, we imagine it being more disordered, not less. But from a cosmic perspective, the early universe was remarkably smooth and uniform. And that uniformity meant it had a very low entropy. There weren't stars or black holes or galaxies, just a dense, nearly featureless sea of particles. And that set the stage for everything that would follow. As the universe expanded, it began to cool. Gravity, acting on tiny variations in density, started to pull matter together. Stars were born, galaxies formed, planets began to swirl around suns. All of this complexity emerged as entropy increased. That's the key. As the universe aged, its entropy climbed steadily upward, and with that climb came the forward flow of time as we experience it. In other words, the Big Bang didn't just start space and time, it also set the direction of time's arrow. That low entropy beginning gave the universe a path to follow, like a marble rolling downhill. If the universe had somehow started in a high entropy state, everything would have been more or less already finished, a soup of maximum disorder, with no structure, no change, no flow. There would have been no arrow of time, no distinction between past and future, no reason for anything to move or evolve at all. But because the Big Bang began in such a special, ordered state, the universe had somewhere to go. Entropy could increase, change could happen, time could flow. Still, this invites a deeper and more uncomfortable question. Why did the universe start in such a low entropy state? After all, there are infinitely more ways for a universe to be disordered than ordered. So why did it begin with such precision? Was it a random chance? A necessity? A hidden law we don't yet understand? Some scientists propose that the Big Bang wasn't the absolute beginning, but a kind of bounce, one phase in an eternal cycle. In this view, the universe expands, reaches a peak, then contracts back into a hot, dense state before bouncing out again in another Big Bang. This could repeat over and over, potentially forever. But even in these models, we're left wondering how the arrow of time works across bounces. Does entropy reset? Does time reverse in a contracting universe? Or does each cycle have its own direction, like pages in a never-ending book? Another possibility is that our universe is just one of many, a bubble in a vast multiverse, each bubble with its own version of time, space, and physical laws. In some of those universes, time might run forward. In others, perhaps it runs backward, or loops, or behaves in ways we can't even conceive. If the Big Bang was simply a local event in a much larger reality, then the beginning of our time may not be the beginning of all time. There could be realms where time flows differently, or not at all. And yet, for us, the Big Bang marks the earliest meaningful point we can talk about. It defines the limits of our cosmic memory. When we look into the night sky, we're seeing light that has travelled for billions of years, light that began its journey not long after that primal moment. The cosmic microwave background, a faint glow still detectable with special instruments, is the aftershock of the Big Bang itself. It's like a photograph of the universe when it was just a baby, only 380,000 years old. That light has been travelling ever since, whispering the story of time's beginning to anyone who can learn to listen. The deeper we look into the cosmos, the further back in time we go. Giant telescopes act like time machines, showing us galaxies not as they are now, but as they were billions of years ago. If we could look far enough, we'd see the universe in its infancy, a roiling, glowing fog of particles, before stars ever twinkled into life. And beyond that, we can't yet see. The laws of physics, as we know them, break down at the very first moments after the Big Bang, at what we call the Planck time, a fraction of a second so tiny it's almost unimaginable. Before that, quantum gravity takes over, and we simply don't yet know how time, space, or matter behaved. It's the ultimate horizon of our understanding. So here we are, floating in the aftermath of a great beginning. A beginning that created not just atoms and light, but minutes and hours, birthdays, sunsets, lifetimes. The Big Bang didn't just set the stars into motion, it gave us the flow of time itself, the rhythm by which we live, remember, and dream. And still we wonder, if time had a beginning, could it have an end? Could it ever slow, stop, or even reverse? And if we could trace the flow of time back far enough, past galaxies, past atoms, past the first burst of light, might we find a moment when time was born from silence, from stillness, from something we do not yet understand? That is the mystery the Big Bang leaves us with. Not just how everything began, but why? And whether the flow of time that began in that first spark might, in some unimaginable way, one day change direction or begin again. Black holes are among the most mysterious and awe-inspiring objects in the universe. They are places where gravity becomes so intense that not even light can escape. But beyond the sensational images of swirling galaxies and collapsing stars lies a strange and profound truth. Black holes do not just bend space, they also bend time. In fact, they offer one of the clearest, most dramatic glimpses into what happens when time slows down, and perhaps how time might behave at its very limits. To understand how black holes affect time, we need to look at Einstein's theory of general relativity. According to Einstein, gravity is not a force in the traditional sense. Instead, it's the curvature of space-time caused by mass and energy. The greater the mass, the more space-time bends. Picture a stretched rubber sheet. If you place a bowling ball on it, the sheet curves inward. Smaller objects roll toward the dip, not because they are being pulled, but because they are following the natural curve of the sheet. Now imagine that curve getting deeper and deeper, so deep that it forms a bottomless pit. That, in essence, is a black hole. Now here's where things get strange. As you approach a black hole, time itself begins to slow down relative to an outside observer. This isn't science fiction. It's a well-tested prediction of relativity, confirmed by experiments and observations. The closer you get to the black hole, the more time slows. From the perspective of someone far away, your clock ticks more and more slowly. If you were to hover just outside the edge of a black hole, called the event horizon, time would appear to nearly stop. To someone watching you from a safe distance, you would seem frozen in time at the edge of the black hole, never quite falling in. But from your own perspective, you would feel time passing normally. You wouldn't notice any difference until you crossed the event horizon. At that point, something truly remarkable happens. Every possible path you could take leads deeper into the black hole. Time, space, direction, these concepts begin to lose their familiar meaning. The event horizon is not just a boundary in space, it is a boundary in time. Inside the event horizon, the geometry of space-time flips in such a way that moving forward in time means moving inward toward the singularity at the centre of the black hole. You cannot stop or turn back, because doing so would mean moving backward in time, and that is no longer possible. You are being pulled inward not by gravity in the usual sense, but by the very structure of time itself. It's as if the singularity is in your future, and you're falling toward it the same way we all move toward tomorrow. You can no more avoid the centre of a black hole than you can avoid the next minute of your life. But here's where the mind truly begins to reel. Could this warping of time near black holes offer clues about reversing time, or at least revealing its hidden dimensions? Some physicists have speculated that the immense gravity of black holes could be used to manipulate time in extraordinary ways. For example, if you were to orbit very close to a black hole without falling in, you could experience time far more slowly than someone further away. This means that when you return from your orbit, far more time might have passed in the outside universe. It's a form of time travel to the future, caused not by speed, but by gravity. This is called gravitational time dilation, and it has been demonstrated even on small scales here on Earth. Atomic clocks at higher altitudes tick slightly faster than those at sea level, because they are farther from Earth's centre of gravity. The idea of using black holes for time travel is a staple of science fiction, but it's grounded in real physics. Some theories even suggest the existence of wormholes, tunnels through space-time, that could, in theory, connect distant points in space and time. If one mouth of a wormhole were placed near a black hole, where time slows dramatically, and the other were kept far away, then a time difference could emerge between the two ends. Step through one mouth, and you might emerge in the past or the future, depending on how the wormhole was arranged. Of course, all of this remains speculative. We don't yet know whether wormholes can exist in a stable form, or whether anything could survive travelling through them. The intense forces inside a black hole, especially at the singularity, where density becomes infinite and the laws of physics break down, may render such travel impossible. And yet, black holes remain our best natural laboratories for studying the extremes of time. They also force us to confront the idea that time is not absolute. There is no single, universal clock ticking away for everyone, everywhere. Time is flexible, changeable, sensitive to motion and mass. In the presence of a black hole, time stretches and twists, slows and stalls. And in doing so, it whispers a profound secret. That time is not the steady river we once imagined, but a malleable, mysterious dimension we are only beginning to understand. Even stranger still is the idea of black hole evaporation. According to physicist Stephen Hawking, black holes are not completely black. They can emit radiation, now called Hawking radiation, and slowly lose mass over time. This process is so slow for large black holes that it's almost imperceptible. But eventually, over eons, the black hole will shrink and vanish. What happens to the information about everything that fell into it? Does it disappear forever, or is it somehow preserved in the fabric of space-time? This question, known as the black hole information paradox, is one of the great unsolved problems in physics. and its answer may reveal even more about the true nature of time. Perhaps the most haunting thought of all is this: what if time, at its core, is not a line, but a web, interconnected, complex, with loops and folds and shadows we cannot yet perceive? What if black holes are not just destroyers of matter, but gateways to deeper truths about time itself? As we drift here under the imagined pull of these dark giants, let us wonder, quietly, gently, what it means for time to slow, to stretch, to nearly stop. Perhaps in the depths of a black hole, where time fades into silence, we come closest to the edge of eternity, and closest to understanding how fragile, how strange, and how beautiful time really is. When we think about time, we often imagine it as something absolute, ticking away in the background like a universal clock that governs all things equally. But in the early 20th century, Albert Einstein shattered that idea with one of the most revolutionary concepts in human history: the theory of relativity. He showed that time is not a constant. It does not move at the same pace for everyone, everywhere. Instead, it bends, stretches, and dances in harmony with space, gravity, and motion. In the strange and beautiful world of relativity, time is not a passive backdrop. It is a living part of the universe itself. Einstein's theory came in two stages. The first was special relativity, introduced in 1905. It focused on observers moving at constant speeds, no acceleration, no gravity. Even in this simplified model of the universe, time revealed its fluid nature. One of the most famous ideas from special relativity is time dilation. The concept that time slows down for objects moving very fast, especially when they approach the speed of light. To understand this, imagine two twins. One stays on Earth, and the other boards a spaceship that travels near the speed of light. The travelling twin zooms through space at incredible velocity, while the one on Earth waits patiently. When the spacefaring twin returns, something strange has happened. Less time has passed for the traveller than for the one who stayed behind. The twin, who remained on Earth, has aged more. This isn't just a thought experiment. It has been confirmed through extremely precise measurements, using atomic clocks aboard airplanes and satellites. Time really does slow down the faster you move. But the story doesn't end there. 10 years later, in 1915, Einstein expanded his theory into something even more profound: general relativity. This new theory included acceleration and, most importantly, gravity. According to general relativity, massive objects like planets, stars, and black holes warp the fabric of space-time. This curvature is what we experience as gravity. And once again, time is caught in the effect. The stronger the gravity, the slower time moves. To grasp this, imagine a clock on the surface of the Earth and another on a mountaintop, farther from the planet's gravitational pull. The clock on the mountaintop ticks just a little bit faster than the one at sea level. This difference is tiny, but measurable, and it's taken into account in the GPS systems that help navigate your phone and car. The satellites that orbit Earth are in a slightly weaker gravitational field and move quickly relative to us. Because of this, their clocks tick faster due to gravity, but slower due to speed. These opposing effects must be corrected constantly so your GPS doesn't lead you astray. In a world ruled by relativity, time becomes deeply personal. It moves at different rates depending on your velocity and your position in a gravitational field. This means that every object, every person, every particle has its own experience of time. There is no master clock synchronizing the cosmos. Instead, time is more like a thread that weaves through each point in space, differently for everyone. Now consider what this means on a cosmic scale. Imagine being near a massive object like a neutron star or a black hole. These celestial bodies are so dense that their gravitational pull is immense. If you were to hover close to one of them, without falling in, your experience of time would slow dramatically compared to someone far away in open space. You could, in theory, spend a few minutes near the edge of a black hole only to return and find that years, decades, or even centuries have passed for others. This is not speculation. It's a consequence of how time and gravity are interwoven. Einstein's relativity also changes how we think about the now. We often believe that there is a single, universal present moment shared by everyone everywhere. But in relativity, simultaneity, the idea that two events can happen at the same time is relative to the observer. Two people moving at different speeds or in different gravitational fields may not agree on what events are happening now. In a very real sense, what you consider the present might be someone else's past or future. This leads to the notion of space-time, a four-dimensional fabric that blends the three dimensions of space with one dimension of time. In this model, time is treated as another coordinate, like height or width. Events are points in this vast landscape. And just as you can move through space, you move through time. But unlike space, we seem to move through time in only one direction, and only forward. Why that is, remains one of the deepest mysteries. The equations of relativity don't forbid time from running backward. They work just as well in either direction. Yet in our experience, time has a direction. We grow older, not younger. We remember the past, not the future. Something beyond relativity, perhaps entropy, perhaps the quantum world, must be giving time its arrow. Still, relativity offers a haunting possibility. Time is not something that flows like a river. It may be that all of time, past, present, and future, exists equally and permanently in the block of space-time. From this viewpoint, our sense of time flowing is just an illusion caused by our consciousness moving through the dimension of time in one direction. We are like travellers on a train, watching the scenery of moments go by, thinking the landscape changes when really it is we who are moving. The past is still there, behind us. The future is already there, ahead of us. But we only see one window at a time. This vision of time, shaped by Einstein's mind, transforms our understanding of the universe and ourselves. It shows us that time is not a rigid, unchanging backdrop, but a flexible, responsive dimension that is shaped by mass, motion, and gravity. It makes us realize that the clock on the wall, ticking away the seconds, is only a shadow of a much deeper reality. And as we float beneath the stars, guided by this new understanding, we begin to see time not as something that slips away from us, but as something we are a part of, woven into its fabric, bound by its rules and yet always reaching forward into its mystery. When we enter the world of the very small, far smaller than atoms, smaller even than protons or electrons, we leave behind the comforting predictability of classical physics and step into a realm that behaves in strange, almost magical ways. This is the domain of quantum mechanics, where particles act like waves, waves act like particles, and reality itself seems to shimmer with uncertainty. And here, in this subatomic universe, time behaves in ways that challenge everything we think we know. In our everyday experience, time moves forward. We wake up, we eat breakfast, we go about our day, cause leads to effect. A ball is thrown, and it lands. A candle burns, and then melts. Time flows in one direction. But at the quantum level, the story becomes far more complicated. Many of the fundamental equations that govern the behavior of quantum particles, such as Schrödinger's equation, are time-symmetric. This means they work just as well if you reverse time as they do if you move it forward. In theory, if you filmed a particle interaction and played the tape backward, you wouldn't be able to tell the difference. The math wouldn't object. This time, symmetry is deeply puzzling because it seems to contradict our experience of the world. Why then do we see such a clear direction to time at the larger scales of reality? Why does boiling water never unboil, even though its molecules obey time-reversible laws? Part of the answer lies in how we observe quantum systems. In quantum mechanics, particles exist in a state of probability. They don't have precise locations or velocities until we measure them. Before measurement, they exist in what's called a superposition, a combination of all possible states. For example, a photon might take every possible path between 2 points, existing in a cloud of uncertainty, until we detect it. Once measured, the wave function, the mathematical description of all those possibilities, collapses into a single outcome. At that moment, probability becomes reality. But this act of measurement seems to introduce something new, a break in time symmetry. Before measurement, the system is time symmetric. After measurement, it's not. Something irreversible has occurred. The question is, why? This problem is part of what physicists call the measurement problem in quantum mechanics. It's one of the great unsolved mysteries in science. Some interpretations, like the Copenhagen interpretation, suggest that measurement causes the collapse, introducing a fundamental asymmetry into the universe. Others, like the many worlds interpretation, propose that the wave function never really collapses at all. Instead, every possible outcome happens in a vast, branching multiverse, and we simply experience one branch. Still others, like the transactional interpretation, toy with the idea that quantum events involve waves travelling not only forward in time, but also backward. According to this view, an emitter sends out a wave forward in time, and an absorber sends a response backward in time. The interaction occurs when both waves meet. If true, this would mean that events in the future can influence the past, a radical and deeply unsettling idea, but one that the math doesn't forbid. This leads us to an even deeper question: is time itself a quantum phenomenon? Could it be that time, like energy or mass, is not continuous but comes in tiny indivisible units, chronons, as some theories propose? If so, Our smooth experience of flowing time might be an illusion, much like how a film appears continuous but is really made up of still frames. Quantum entanglement adds another layer of strangeness. When two particles become entangled, they share a connection so deep that the state of one instantly influences the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to happen faster than light, and possibly outside the normal flow of time. If a measurement made here can affect a particle across the galaxy immediately, what does that say about time? Are these changes happening now, or is our concept of now too narrow to capture what's really happening? Some physicists believe that entanglement could hold the key to understanding time itself. They suggest that the fabric of space-time, including time as we know it, might emerge from the web of quantum entanglements between particles. In this view, time is not fundamental. It's not something the universe is built on. It's something that emerges when enough particles become connected in the right way. Like a melody arising from notes, time arises from relationships. This idea is still very much in development, but it hints at something profound. Time might not be built into the universe at all. It might be something the universe does. This idea also touches on the so-called arrow of time. If the basic equations of quantum mechanics are time symmetric, why does entropy increase? Why does the universe evolve in one direction and not the other? Some researchers believe the answer may lie in quantum decoherence, the process by which quantum systems interact with their environments and begin to behave classically. When a quantum particle becomes entangled with the surrounding world, its behaviour starts to follow the familiar arrow of time. The pure symmetry of the quantum world becomes smeared out into the irreversible flow we experience every day. But what happens at the edge of quantum and gravity? Here we enter the murky territory of quantum gravity, a field still waiting for a full theory. Black holes, again, offer a natural laboratory. At their centres, known as singularities, both quantum mechanics and general relativity break down. Time becomes meaningless, or perhaps infinitely curved. In such extreme environments, time may behave in ways we cannot yet imagine. It might loop, twist, split, or vanish entirely. Some theories, like loop, quantum gravity, or string theory, attempt to describe what happens at these edges, but no consensus has yet emerged. And what about consciousness? Some have speculated that human awareness plays a role in shaping time at the quantum level. This is highly controversial and veers into the philosophical, but it raises compelling questions. If observation affects quantum outcomes, and if time depends on those outcomes, then could our very act of being aware help shape the direction or structure of time? This isn't a scientific conclusion, but it is a poetic one. Ultimately, quantum physics reveals that time is not what it seems. It is not absolute. It is not linear. It is not even necessarily flowing. At the deepest levels of reality, time becomes a ghost. Something we glimpse. Something we use. But something we may never fully grasp. It is a mystery that hides in the behaviour of the tiniest particles, whispering secrets through entangled threads and shimmering waves. As we sit quietly beneath the stars, listening to the hum of the quantum world, perhaps we can begin to see time not as a ticking clock, but as a symphony of possibility, uncertain, unpredictable, and infinitely strange. One of the deepest and most puzzling questions in physics is whether time is truly symmetrical. Can time run both forward and backward equally, or is its one-way flow, what we call the arrow of time, an unbreakable rule? At first glance, the world appears stubbornly asymmetric. We remember yesterday, not tomorrow. We can crack an egg, but not uncrack it. Yet when we peel back the layers of nature, when we look closely at the fundamental laws that govern particles and fields, we find a strange and beautiful symmetry hiding underneath. In physics, symmetry is not just about things looking the same on both sides of a line or an object. It refers to the deeper invariances in the equations that describe how the universe behaves. Time symmetry, or time reversal symmetry, means that if you took the equations of motion that describe a system and reversed the direction of time, changing every t to a t, those equations would still work just fine. They would continue to describe a valid version of reality. This is true for many of the laws that form the bedrock of physics. Newton's laws of motion, time symmetric. Electromagnetism, as described by Maxwell's equations, also time symmetric. Schrödinger's equation in quantum mechanics, time symmetric again. Even Einstein's theory of general relativity, the grand framework that describes how space and time bend under gravity, allows time to move in either direction. The equations do not choose a side. They do not demand a future or a past. They allow both. And yet, we never see time running backwards. In everyday life, we see broken cups, not unbroken ones. We see smoke rise, not return to the fire. We age, and we never grow young again. This divide between the symmetric world of equations and the asymmetric world of experience is one of the greatest philosophical and scientific mysteries we face. If the laws of physics allow time to run backwards, why does reality insist on running forward? The main explanation, as we've seen in earlier chapters, is entropy. The second law of thermodynamics tells us that in a closed system, entropy, the measure of disorder, tends to increase. This increase in entropy gives rise to the arrow of time. It separates past from future. Even though the microscopic laws governing atoms and particles are time symmetric, the probability of reversing the chaos of the macroscopic world is so low that it becomes, for all practical purposes, impossible. But there's more to the story. In the world of particle physics, time symmetry is not just an abstract idea. It is connected to something called CP symmetry. C stands for charge, meaning the swapping of particles with their opposites. Electrons with positrons, for example. P stands for parity, which is like flipping the universe in a mirror. If the laws of physics are the same, when both charge and parity are reversed, we say they are CP symmetric. And according to a principle called CPT symmetry, if we reverse charge, parity and time, the laws of physics must stay the same. But in 1964, physicists observed something strange. A certain type of subatomic particle, called a kaon, did not behave the same when time was reversed. It showed a tiny but measurable violation of time symmetry. This discovery, known as T violation, was a seismic shock to the physics community. It meant that even at the fundamental level, the universe may not be completely time symmetric. Since then, more examples of T violation have been found in other particles, like B mesons. These violations are subtle. They don't overthrow the entire framework of physics, but they hint at something deeper. They suggest that time's arrow might not just emerge from entropy, but may be etched into the laws of nature at the most basic level. That the universe may, in some sense, prefer moving forward in time, even in its tiniest building blocks. This discovery has huge implications. For one, it might help explain why the universe exists in the first place. One of the great mysteries of cosmology is why there is more matter than antimatter in the universe. At the moment of the Big Bang, matter and antimatter should have been created in equal amounts, and then promptly annihilated each other. Yet somehow, matter won. The slight imbalance allowed stars, planets, and people to exist. T violation may be one of the keys to understanding how that imbalance arose. In this sense, the universe's asymmetry in time could be linked to our very existence. But even as we uncover these asymmetries, the broader question remains: is the universe fundamentally time-symmetric or not? Some physicists believe that time symmetry is still a deep truth, that the apparent flow of time is a result of our perspective, our memory, our location in a low-entropy universe. Others think that time might have an intrinsic direction, that the arrow of time is not an illusion, but a law. This debate plays out in different interpretations of physics. In the block universe model, past, present, and future all coexist. Time doesn't flow, it is. Every moment exists forever, and the illusion of movement is just that, an illusion. In this view, time symmetry reigns. There is no special now, and no need for time to prefer one direction. Other theories, like the thermal time hypothesis, suggest that time emerges from the statistical state of the universe. In a state of perfect equilibrium, where entropy is maximized, time ceases to exist. There would be no way to tell which direction is the future and which is the past. Time, in this view, is a side effect of disequilibrium. As the universe cools and becomes more balanced, time might fade away entirely. Still, the symmetry of time remains a haunting, beautiful idea. It whispers of a world where moments are reversible, where choices could be unmade, where cause and effect blur together in a dance beyond our comprehension. And yet, the universe keeps reminding us, this is not the world we live in. We are creatures of the forward-flowing river. Our memories grow, not shrink. Our bodies age, not rewind. The sun sets, never rises backwards. But the symmetry still sings, just beneath the surface. In every bouncing atom, every field of energy, every quantum leap, the past and future are more alike than we dare to admit. Perhaps then, the universe holds both truths at once. A deep, hidden symmetry beneath a world of irreversible moments. A perfect, timeless balance beneath the unfolding story of stars, life, and dreams. And as we lie still, listening to the quiet hum of time all around us, we might find peace in that paradox, that the universe is both eternal and fleeting, both forward and backward, both symmetrical and not. A mystery endlessly unfolding in every moment we call now. Time travel is one of the most enduring dreams of science fiction and human imagination. The idea that we could step into a machine, press a button, and journey into the past, or leap into the far future fascinates us because it touches something deep within, our longing to undo mistakes, to revisit lost moments, or to witness things beyond our lifetime. But is time travel possible? Could the laws of physics ever allow such a thing? Surprisingly, the answer is maybe. Not only does time travel not outright violate the known laws of physics, it may even be hidden within them. To begin exploring this idea, we need to return once again to Einstein's theory of general relativity. In his revolutionary vision, time is not separate from space, but intimately woven into it. Together, they form a four-dimensional fabric called space-time. Massive objects like planets and stars bend this fabric, creating what we experience as gravity. But in the right circumstances, this warping can become extreme. Space-time can twist, stretch, and even loop back on itself. And when it does, the possibility of time travel begins to emerge. One of the most intriguing features in general relativity is something called a closed time-like curve. This is a path through space-time that loops back to the same point in space and time, a journey that could, in theory, allow an object to return to its own past. Certain solutions to Einstein's equations, such as those involving rapidly rotating black holes or hypothetical structures called wormholes, suggest that these closed loops could exist. In essence, if you could find or create such a path, you might be able to step into it and emerge at an earlier moment in time. Let's imagine a wormhole, a tunnel that connects two different points in space and time. One mouth of the wormhole could be placed near a strong gravitational field, like the edge of a black hole, where time moves slowly. The other could remain far from any such influence, where time flows more normally. If you travel through the wormhole from the slow end to the fast end, you would emerge in the past relative to when you entered. This setup creates a time machine, at least in theory. Of course, theory is one thing, reality is another. Wormholes, if they exist at all, may be highly unstable. They might collapse the instant anything tries to pass through them. To keep them open, you would need something called exotic matter, a form of matter with negative energy density. This kind of matter has never been observed, though it's allowed in some interpretations of quantum theory. If exotic matter exists and could be harnessed, it might make stable wormholes possible. There's also the concept of time dilation as a form of time travel, not to the past but to the future. As we've seen, time moves more slowly for objects travelling at high speeds or in strong gravitational fields. This means that astronauts orbiting Earth experience time just a bit slower than people on the ground. If we could build a spacecraft that travelled close to the speed of light, someone aboard it could make a round trip and return to find that centuries had passed on Earth. This is not science fiction. It is a proven consequence of Einstein's special relativity. We've even observed it in high-speed particles and satellite clocks. But backward time travel, the kind where you visit the past, is far more complicated and fraught with paradoxes. The most famous of these is the grandfather paradox. Imagine you travel back in time and accidentally prevent your grandfather from meeting your grandmother. If that happens, you could never be born, and therefore could never have travelled back to begin with. This logical contradiction challenges our understanding of cause and effect. It suggests that if backward time travel is possible, it must come with rules. rules that preserve consistency, perhaps by preventing changes to the past, or by splitting reality into alternate timelines. Some physicists propose that the universe has a built-in consistency safeguard, that any events resulting from time travel must be self-consistent. This is known as the Novikov self-consistency principle. According to this idea, no matter what you do in the past, you can't change the present in a way that creates a paradox. Your actions in the past become part of history and were always meant to happen. You might think you have free will in the past, but everything you do there would ultimately support the timeline that already exists. Others take this even further, suggesting that time travel might result in the branching of realities. In the many-world interpretation of quantum mechanics, every possible outcome of every event exists in a vast multiverse of parallel worlds. If you travelled into the past and altered something, you wouldn't be changing your original timeline. You'd be creating a new branch, a parallel universe where events unfolded differently. Your own history would remain intact, and you would simply find yourself in a new reality. These ideas are breathtaking, but they remain speculative. We have no experimental evidence of backward time travel. We don't know if wormholes are real. We don't know if the universe would allow closed time-like curves to persist, or if some deep principle, like quantum effects or causality, would prevent them from forming. Still, physicists continue to explore these ideas, not because they expect to build a time machine tomorrow, but because time travel touches the very structure of the universe. By asking whether time can be reversed, or whether we can travel through it, we are really asking what time is. Is it a dimension, like space? A process? An illusion? A limitation of consciousness? Time travel forces us to confront these questions head-on, and perhaps, in some ways, we already travel through time. Every moment that passes carries us from the past into the future. Our memories are windows into what was. Our hopes and fears project us forward into what might be. In dreams and stories and imagination, we revisit the past and leap into the future effortlessly. Maybe one day we'll learn to move through time the way we move through space, deliberately, precisely, with understanding. Or maybe time is more like a river we must follow, unable to swim upstream, but always wondering what lies around the next bend. As you listen to these thoughts beneath the gentle rhythm of stars and silence, consider this. Time travel may not be about machines or paradoxes. It may be about awareness, about how we relate to the flow of moments, about how we carry the past within us and plant the seeds of the future with every action we take. In the end, time travel might not be something we do with gears and engines. It might be something we do every time we remember or dream. Throughout history, storytellers, artists, and dreamers have imagined worlds where time doesn't follow the simple rules we know. In these worlds, people leap across centuries, glimpse the future, or change the past with a single decision. From ancient myths to modern science fiction, the idea of reversing time, of undoing what's been done, has captured the human imagination in profound and poetic ways. But how does the concept of reverse time in fiction compare to what science actually tells us? And what do these stories reveal about our deeper desires and fears? Let's begin with the myths. Long before physics existed as a discipline, cultures around the world were already grappling with time's mystery. In Hindu philosophy, time is cyclical, a vast wheel that turns eternally through creation, destruction, and rebirth. The universe is born, unfolds, fades, and then begins again. In ancient Greece, the god Kronos represented time as an unstoppable force, while Kairos symbolized the right or opportune moment, hinting that not all time is created equal. These early concepts treated time not as a straight line, but as something layered, sacred, and mysterious. Fast forward to modern times, and the idea of reversing time becomes a central theme in countless stories. In Charles Dickens' A Christmas Carol, Ebenezer Scrooge is shown his past and future by spirits, not so he can change the timeline, but so he can change himself. Time becomes a mirror, a moral compass. It doesn't need to reverse to offer redemption. It just needs to be seen. In H.G. Wells' The Time Machine, time is a literal dimension the protagonist can travel through, much like space. The machine allows him to leap forward into strange futures, bypassing centuries in a blink, revealing how the future might evolve if present conditions go unchanged. Then came the golden age of science fiction, stories where time became a playground for possibility and paradox. In Ray Bradbury's A Sound of Thunder, a small change in the distant past, stepping on a butterfly, ripples forward to alter the present dramatically. This story introduced the idea of the butterfly effect, now a staple of time travel fiction and chaos theory. It suggests that time is delicate, interconnected, and dangerously mutable. In contrast, in films like Back to the Future, characters interact with their own histories, sometimes altering the future, and sometimes being forced to preserve it. These stories balance entertainment with deep questions. Are we free to change time, or are we bound by it? Can we rewrite our destinies, or are they etched in cosmic stone? More recently, films like Tenet have explored the idea of time inversion, where objects and people experience time in reverse while the world around them moves forward. In that world, reverse time isn't just a narrative device, it's a physical process, with bullets unfiring and events unfolding backward. Watching it challenges our perception of causality. If something happens in reverse, is it still an effect? If the future can influence the past, then what becomes of free will? Stories like these, while fictional, often mirror scientific ideas, albeit in exaggerated or metaphorical ways. The notion that tiny actions can have enormous consequences echoes the sensitivity of chaotic systems in physics. The idea of time travel as a loop, seen in movies like Looper or Predestination, echoes concepts from general relativity and closed time-like curves, and the fantasy of changing the past often reflects a deeply emotional truth: our desire to heal, to fix, to make right what once went wrong. But while fiction embraces these possibilities, science remains more cautious. As we've explored, the fundamental laws of physics often appear time-symmetric, meaning they don't care whether time moves forward or backward. This opens the door to theoretical models where reverse time is possible. However, the macroscopic world we live in is not symmetrical in this way. Entropy always increases. Glass breaks, but doesn't unbreak. Life moves forward. Memory stores the past, not the future. Science fiction often skips over this thermodynamic truth because it's narratively inconvenient, but it remains one of the greatest obstacles to actual time reversal. And yet, fiction isn't wrong to dwell in the spaces science cannot yet reach. Sometimes, stories are experiments too, just written in different ink. They test ideas not with equations, but with characters. They ask, what would it mean to reverse time emotionally? If you could return to the moment before a loved one died, would you relive it? Would you try to stop it? Would it be the same, or would it change you forever? These questions are not about physics. They're about longing. Many time reversal stories are built on regret. They speak to our human need to make sense of loss. To believe that things could have gone differently, if only we'd acted sooner. If only we could go back. This emotional core makes these stories powerful, regardless of whether they make scientific sense. They reflect a universal truth. We all wish, at times, that we could undo the irreversible. But some stories also imagine reverse time as a kind of enlightenment. In the film Arrival, time is non-linear. The protagonist begins to experience her life out of order, future memories mixing with past events. This shift allows her to see her life differently. She accepts pain and joy alike because she sees their place in the whole. In this vision, reversing time isn't about escape. It's about understanding. In this way, fiction gives us a way to live inside time's mystery. It lets us imagine what it would feel like to experience time backward, not just physically, but emotionally, spiritually. It dares to ask, what if everything is already written? What if every moment is already eternal? What if reversing time isn't about movement, but about perspective? From a scientific standpoint, we are far from turning these dreams into reality. But the boundary between science and story is more porous than it seems. Fiction dares to ask questions that science is not yet ready to answer. And science, in turn, sometimes finds truth in places that fiction first imagined. So as we listen to the ticking of the universe, steady and strange, let's not dismiss the tales we tell of reverse time. For even if the clock never truly runs backwards, these stories remind us of something vital. That time is not just a measure of seconds and hours, but a vast and delicate experience. A mirror, a maze, a mystery. And in our search to understand it, every story, every theory and every heartbeat has a place. Imagine waking up tomorrow and realizing that your memories are playing in reverse. You remember tomorrow before today. Your first kiss is still ahead of you, but the end of a long relationship lingers in your heart like a faint echo from a life that hasn't happened yet. You see a flower unwilt, a teardrop return to an eye. A book unread itself word by word. The world, to your senses, is perfectly familiar, but your direction through it has changed. You are now living backward. This is not just a curious idea. It is a deeply unsettling and profound inversion of everything we associate with identity, meaning, and memory. Living backward challenges the core of what it means to be human. We define ourselves through our stories, and stories unfold in time. If time were to reverse, how would we know who we are? How would we understand cause and effect, growth, love, pain or purpose. In our ordinary experience, memory provides the structure of the self. We remember childhood, not old age. We learn from mistakes made in the past, not from wounds that have not yet been inflicted. But in a reversed time life, memory would function in a strange and unfamiliar way. You might remember dying before you were born. You would anticipate pain before the cut. You would be comforted before the sorrow, laugh before the joke, celebrate before the victory. Would this make life more painful or more peaceful? Consider a backward life as a kind of rewind through experience. If you begin with death and move toward birth, do you experience the undoing of life's tragedies? Do regrets become comforts as your actions reverse and your choices untangle themselves? You might see loved ones reappear after years of absence. Watch wrinkles fade from your parents' faces. Hear familiar voices grow stronger and clearer with time. But each reunion would bring the silent ache of knowing, if you're aware, that they are not returning permanently. They are unleaving. The joy would be bittersweet, because you would experience healing only by undoing the journey that created the love in the first place. In such a world, causality would feel alien. You might take an action and see its effects appear before you make the choice. Responsibility would be confusing. Did you decide to say those words, or were you simply playing them out in reverse? Is your apology sincere if it precedes your mistake? Do you learn from experience, or does experience retreat from you, slipping through your fingers like an unravelling thread? And what of growth, perhaps the most human part of all? In reverse time, you would lose knowledge instead of gaining it. Wisdom would fade. You would gradually forget what you've learned, unlearn habits, unacquire skills. You would grow less articulate, less precise, less aware. And yet, in a strange twist, you would move toward innocence. You would gradually shed the scars of life. Emotional wounds would close. Grudges would dissolve. Fears would vanish. You would become lighter, not through spiritual awakening, but by moving away from the weight of lived experience. But would that be a blessing or a loss? Our sense of meaning often comes from struggle. We cherish things because we know they are fragile, temporary, and hard-won. A life that moves forward is filled with unknowns, with anticipation, with choice. A backward life, on the other hand, might feel like a performance already written. Even if the moments are joyful, they come with the faint awareness that you are returning them to the shelf, one by one, rather than discovering them anew. Language itself would change. You might speak words and only afterward feel the impulse that caused them. You would feel laughter as the echo of a joke, not its result. You would experience sorrow before the event that caused it. Relationships would be difficult to interpret. You'd meet someone and immediately feel distant, only to grow more intimate as your shared time dwindles. And just as closeness peaks, you forget them. Their name, their face, their role in your life. Gone, like a letter burned in reverse. Would love, in such a world, feel less or more real? Perhaps it would be purest in its final moments. Your last day with someone, which, in this world, is your first meeting. You wouldn't know their history. You wouldn't carry any of the baggage that normally weighs relationships down. You would encounter them with open arms, open eyes, and no past to interfere. Maybe that is what true presence feels like. A moment unburdened by memory. Still, the sorrow would remain. Because in this reversed life, every hello is a goodbye, and every embrace is a letting go. Time does not allow you to stay. It carries you away, not toward a future, but away from it, toward simplicity, silence, and eventually non-existence. And at the very end, when you are small, when you can no longer speak, when your senses dim and fade, you return to the soft warmth of the womb. The noise of life disappears. There is peace. No more questions, no more choices, no more memories. You return to the point before you knew you were alive. But if you were conscious of this reversal, if you could retain awareness through the entire journey, it might transform your understanding of life entirely. You would see the shape of a life not as a rising curve, but as a falling arc of return. You would realize that nothing lasts, but everything matters. That time does not steal from us, but lends us experiences to hold, briefly, tenderly, before they pass on to someone else. To live backward would not be easy. It would disorient the mind and challenge the heart. But it might also offer a perspective we cannot see from our one-way path. That time is not a straight road, but a vast landscape we only explore in one direction. That every moment is both a beginning and an end, both arrival and departure. And maybe, in the stillness of that reverse journey, we would learn the most important truth of all. That life is precious not because it moves forward, but because it moves at all. That whether we are coming or going, loving or leaving, remembering or forgetting, we are here, now, suspended in this strange, beautiful thing we call time. And that is enough. To imagine living backward is to step into a reality that turns everything familiar on its head. Life, as we know it, is a journey of growth, physically, emotionally, and mentally. From infancy to adulthood, we accumulate experiences, memories, knowledge, and connections. We build our identities around the narrative of change and progress. But what if, instead of growing older, we began by knowing everything and gradually shed that understanding? What if, instead of moving from innocence to experience, we move from experience back to innocence? In this reversed life, the usual milestones that define human existence, learning to walk, speaking the first words, falling in love, building careers, facing loss, would all unfold backwards. We would start with the fullness of knowledge, relationships, and emotion, only to see them dissolve step by step. This would be like watching a movie played in reverse, where every event leads to its origin instead of its consequence. Such a life would challenge every assumption about identity. Would you still be you if your memories faded away, if your connections unravelled, if your skills disappeared? In our normal experience, memory and learning are what anchor us. They give continuity to our selfhood. But in reverse time, the self might be something fragile, constantly slipping away, unravelling like a thread being pulled from a tapestry. The emotional experience of such a life would be profoundly different. Instead of anticipating the future, you might instead anticipate loss. Instead of building bonds, you'd watch them unwind. Joy would become a prelude to sorrow. Laughter would follow sadness. This inversion forces us to confront what we value most. How much of our happiness is tied to hope, to expectation, and to the unfolding story of our lives. Yet there is a paradox here. While knowledge and connection fade, the return to innocence might bring a different kind of peace, a shedding of burdens, regrets, and pain. The unknowing that children often experience, free from the weight of memory and the anticipation of the future, might become the ultimate refuge. This backward journey could be seen as a path toward purity, simplicity, and freedom from suffering. As we move from this vision of a backward life, let's turn to a question that ties deeply into the nature of the universe itself. Will the universe ever reverse its course? Will the arrow of time, which has carried everything from the fiery birth of the cosmos to the present moment, ever flip direction? Our current understanding of cosmology paints a universe that began in the Big Bang and has been expanding ever since. This expansion seems to be accelerating, driven by a mysterious force called dark energy. If this acceleration continues indefinitely, the universe will keep expanding forever. Stars will burn out, galaxies will drift apart, and the cosmos will grow colder and emptier, a scenario often called the heat death. In such a future, entropy reaches its maximum, and the arrow of time continues pointing forward, but toward a quiet and lifeless cosmos. But some theoretical models imagine a different fate. What if the expansion slows and reverses? What if gravity eventually wins, pulling everything back together in a colossal contraction called the Big Crunch? In this scenario, the universe would shrink back to an incredibly dense, hot state, perhaps even reaching conditions similar to the Big Bang, but in reverse. If such a contraction were to occur, would time itself run backward? Would entropy decrease? Would the arrow of time reverse direction? The physics here is complex and uncertain. Some cosmologists suggest that the arrow of time is tied directly to the expansion of the universe. If the universe contracts, time's arrow might reverse. The future would become the past, and the past the future. This implies that all the processes we associate with time moving forward, aging, cause and effect, memory, would flip as well. Yet other models argue that time's arrow is more deeply rooted, perhaps tied to initial conditions set at the Big Bang that are independent of expansion or contraction. In this view, even in a contracting universe, time would continue flowing forward from our perspective. The physical processes might behave differently, but the direction of cause and effect would remain unchanged. Either way, the idea that the universe itself might experience a reversal of time's arrow is a profound and humbling one. It suggests that time is not absolute, but connected to the grandest scales of reality. It reminds us that our experience of time is woven into the fabric of the cosmos itself. Finally, as we contemplate the mysteries of time, its direction, its flow, its meaning, we return to a simple but profound truth. The present moment is a gift. Time's arrow, with all its mystery and complexity, brings us to now. The beauty of now is that it is alive with possibility. It is the moment where past and future meet, where memory and anticipation merge, where we have the power to act, to love, to create. Though time may flow forward relentlessly, carrying us through change and loss, it also gives us the chance to grow, to connect, to find meaning. Without the arrow of time, there would be no stories, no journeys, no evolution. There would be only stillness. Yet within this stillness lies the mystery of existence. Time teaches us that everything is fleeting. Moments pass like waves on the shore, never to return, yet always part of the greater ocean. The knowledge that time moves forward, and not backward, makes every breath, every smile, every tear precious. So as we lie beneath the vast expanse of stars, let us embrace the flow of time. Let us find peace in its passage, wonder in its mystery, and gratitude in its gift. For time may be fleeting, but it is the thread that weaves our lives into a tapestry of meaning. It is the rhythm that carries us forward, ever onward, toward the unfolding horizon of being. And in that journey, no matter which way time might bend or twist in the distant cosmos, we find the deepest truth of all, that life, in every moment, is enough.